Most people think that quantum computing is some abstract, futuristic technology buried in research labs. But what if I told you that companies like IBM, Google, and Microsoft are already building quantum systems today? And that businesses that ignore this shift might be left behind? In this video, we're unpacking the world of quantum computing, what it is, why it matters, and how it's already beginning to change everything from finance to cybersecurity, drug discovery, and machine learning. If you've heard buzzwords like qubits, superposition, or quantum supremacy, but never really understood what they mean, don't worry. By the end of this video, you'll not only understand them, but you'll see why some experts are calling this the biggest revolution in computing since the microchip. Let's start with the basics. All the devices you've ever used, from your phone to supercomputers, operate on classical computing. Classical computers process data using bits, which can be in one of two states, 0 or 1. It's binary, and everything digital today is built on that foundation. Quantum computers, on the other hand, use qubits. And this is where things get weird. Qubits can be both 0 and 1 at the same time, thanks to a principle called superposition. This allows quantum systems to process many possibilities at once, rather than one at a time. It's like the difference between checking every key on a keychain one by one versus trying all of them simultaneously. Quantum computing doesn't just aim to replace classical systems. It's designed to solve problems classical computers physically can't handle, no matter how powerful they get. That's why industries are watching closely. So let's zoom in. What exactly is a qubit? A qubit is the quantum version of a classical bit, but instead of storing information as a binary value, a qubit can exist in a superposition of states, meaning it holds both 0 and 1 at the same time, until it's measured. Qubits also interact through a phenomenon called entanglement, where the state of one qubit instantly affects another, even if they're far apart. This enables powerful correlations that classical computers can't replicate. Qubits can be created in different ways, using trapped ions, superconducting circuits, photons, and even topological materials. Each method has its own pros and cons, but they all aim to unlock the same thing: unprecedented computational power. A quantum computer is like a giant, fragile orchestra of qubits that must stay in harmony. Inside a quantum processor, qubits are carefully maintained at near absolute 0 temperatures to minimize interference. They're manipulated with lasers or microwave pulses to perform quantum operations, known as quantum gates. Quantum algorithms, like Shor's algorithm for factoring large numbers or Grover's algorithm for database searching, leverage the power of entanglement and superposition to perform tasks that would take classical systems millions of years. But building quantum computers is incredibly hard. Even the slightest vibration or heat can collapse a qubit's state, a process called decoherence. That's why maintaining quantum stability is one of the biggest engineering challenges today. In 2019, Google claimed quantum supremacy, saying their 53-qubit machine, Sycamore, solved a problem in 200 seconds that would take a classical supercomputer 10,000 years. It was controversial, but it marked a major milestone. IBM, meanwhile, is focused on making quantum more practical. They've built machines like the Eagle and Condor processors with over 100 qubits, and they've created the IBM Quantum Network, giving researchers, startups, and enterprises access to quantum hardware via the cloud. Microsoft is investing in a more scalable approach, topological qubits, aiming for long-term error correction and real-world deployment. They're also building Azure Quantum, a platform that allows hybrid classical quantum computing. These aren't proof-of-concept projects anymore. Billions are being invested. The race is on, and it's accelerating. So why are companies, from finance to pharma, so interested? Because quantum advantage is real. Companies that tap into it early could gain massive competitive edges in everything from portfolio optimization to logistics routing to drug molecule simulations. Some banks are already experimenting with quantum to detect fraud patterns that classical systems miss. Logistics companies are modeling complex delivery routes. Drug developers are testing molecule folding simulations for new medications. And governments are getting involved too, with quantum research now tied to national security, cryptography, and defense technology. Whoever leads in quantum leads in data. Let's break down some of the industries that quantum computing is set to fundamentally change, not just by making them faster, but by unlocking solutions that were previously impossible. Pharmaceuticals. Quantum computers can simulate molecular interactions at the atomic level, something classical computers struggle with due to sheer complexity. This could dramatically accelerate drug discovery, reduce development costs, and even help in creating custom treatments for complex diseases. finance, from portfolio optimization to fraud detection. Quantum algorithms can process vast data sets and probability spaces in ways that classical systems can't. This means more accurate risk models, faster simulations of market behavior, and smarter decision-making for everything from hedge funds to retail banks. Logistics and manufacturing. Complex supply chain problems, factory routing, and resource distribution often involve millions of variables and constraints. Quantum's ability to evaluate many possibilities at once can make these tasks far more efficient, saving both time and cost while boosting reliability. Artificial intelligence, quantum machine learning could supercharge current models, enabling faster training times and more efficient pattern recognition. Certain AI tasks that are bottlenecked by data volume or dimensionality could see breakthroughs in both speed and accuracy. Cybersecurity. Quantum computers pose a threat to today's encryption methods, particularly RSA and ECC, but they also open the door to quantum-safe cryptography, including lattice-based encryption and quantum key distribution. This is a double-edged sword. Governments and tech companies are now racing to rethink the future of secure communication. Quantum computing isn't just an upgrade to current systems. It's a paradigm shift that may redefine what's computationally possible across almost every data-driven industry. But let's not get ahead of ourselves. Quantum isn't perfect. It's still early. Current quantum computers are noisy, have limited qubit counts, and need extreme environments to operate. Algorithms are in development, but few have real-world, error-corrected implementation yet. And then there's accessibility. How do small businesses or individual researchers tap into this tech? Right now, it's mainly large corporations and elite universities. But platforms like IBM Quantum, Azure Quantum, and Amazon Bracket are starting to open the door. Here's what you should be watching for next. 1,000 plus qubit systems with error correction. Quantum cloud platforms becoming standard in enterprise software. Hybrid algorithms that combine classical plus quantum processing. Quantum-resistant cryptography being rolled out. National quantum strategies from major governments. We're entering a phase where quantum isn't just theoretical, it's practical. And those who move first will shape the way forward. Quantum computing is complex, yes, but it's not something you can afford to ignore. If the microchip defined the last century, quantum may define the next. And right now, companies and governments are already placing their bets. So whether you're a developer, investor, student, or just a curious mind, this is your wake-up call. Learn it now, because soon it won't be optional. Thanks for watching Tech on the Mind. Hit that like button, subscribe, and let us know in the comments. Where do you think quantum will hit hardest first? Medicine, money, or machine learning?